So I want to talk about a programming language that I designed as part of my bachelor in computer science that I was doing on the side, my PhD study program. And yeah, as you can see, that the title CQ, I really like C, in case you know it, like the classical programming language. And I want to do a C-style programming language which I can express classical concepts, but also quantum programming concepts in one unified framework, and ideally sharing a lot of syntax, right? Not just you have a classical part and you have a quantum part and they don't really talk to each other, but instead you have one program where you can use them, so to say, intertwined, interleaved, and reuse classical syntax also for quantum variables, for quantum functions, whatever, wherever it makes sense. You will see in a few minutes. So the emphasis is really on the Q, but it should still or mostly focus on classical syntax and classical concepts, and rediscover them whenever possible, not to reinvent the wheel for everything. As I said, that was part of a bachelor thesis I completed beginning of this year. I had to check the date. Here's a QR code in case you're interested. I will also show it at the end of the talk. And I did this bachelor thesis at the Institute for Theoretical Computer Science with Professor Heribert Vollmer. And even though it was a rather practical work, I would say, because I also wrote a lot of code for it, it was still good that I was at this very theoretical department, because he helped me also a lot and gave good insights about like structure of Boolean functions, how to deal with them more formally. And you will see that later on, this will also appear once or twice in the algorithmic or in the language design. But it was a very nice project, I would say. The main motivation for me actually was I wanted to, I'm studying a lot in my PhD program. I'm studying a lot Grover's algorithm and variants of it. And I think it's an amazing, broadly applicable framework. But it's like it was conceived for a classical problem, namely unstructured search, right? In a classical list, there was nothing quantum about the problem formulation itself. Just the algorithm itself has quantum subroutines, but the problem is classical. But what I was missing really was in these existing frameworks a nice way of expressing Grover's algorithm with these classical concepts, not so much on a gate by gate basis. We will see also that a bit later. So we'll just briefly recap Grover's algorithm and some variants. I think you're mostly familiar with all of them, so we'll not dive into much detail, but just as a broad overview / motivation for that language. As being said, it's let me try that out also. Idea was, okay, unstructured search. I have M elements that are somehow marked. So I have an oracle that tells me this item is the one I'm interested in, this is what I'm searching for, and I have N total items in my list. Now I want to, and I have no further structure. Now I want to search for one of these M items. Classically, the best thing is I can do is to just go through a list one by one, check whether the oracle evaluates to true on an item, then if it does so, return that item, because there's no further structure. Now with Grover's algorithm, at least asymptotically, I can do that faster, namely with this famous square root speed up, right? It's square root over n over m. And it doesn't really have practical relevance for this task, because when do you do unstructured search? Most databases are structured, sorted, whatever. Then you do binary search, which is way faster than Grover's algorithm. But the main idea is amazing. And the main idea can be extended to other problems where you don't have, in practice, something like you sorted your database and you do binary search. For example, what I cooked up for the theoretical computer science guys was this one. Let's say you want to solve the task of sampling uniformly from all prime numbers smaller than n. I don't know, might be relevant for some cryptography stuff, I don't know. So classically, what you could do is you could do the sieve of Eratosthenes. This should give you a list of all the prime numbers smaller than n that scales linearly with n and has some logarithmic factors hidden in this notation. What you could do quantumly is instead you can quantize some of these primarily tests you use for determining whether something's a prime number or not. You can directly quantize them, use those as an oracle, and then use Grover's algorithm to boost the amplitude of all these prime number states. So all the computational basis states that correspond to prime numbers. And then you simply don't measure. So as long as you don't measure, you retain that nearly uniform superposition over all prime numbers. And again, at least asymptotically, that's faster. Again, hiding logarithmic factors, but this scales again with square root of n. In terms of oracle calls to these primarily tests, that's very important. So this was a rather made-up example, but there are more concrete examples. Grover's algorithm is also used in combinatorial optimization. What you can simply do is you can wrap around a big for loop or a big while loop around Grover's algorithm. Let's say start with an initial solution. This gives you some threshold. Let's say you want to do minimization. Then you simply substitute as the oracle in. You compare the objective value of your solutions to the current threshold. And if it's lower than that, then you boost the amplitude of this with Grover's algorithm. Then you do that once, you measure, you get a new solution. Ideally, it's better than the previous one, and you update your threshold. And do that again and again and again until you either found the optimum. In that case, you don't know whether you found the optimum, right? So you need also some break condition in the end that you don't idle forever. Or so let's say the parameters were not well tuned enough that you made it through the optimum, but you have an successive increase or decrease in that sense in the objective value. That's called quantum minimum finding. Another thing is solution counting, if you're familiar with quantum amplitude amplification, which is basically direct generalization of Grover's algorithm, just with non-uniform superpositions. In the same paper, they also introduce quantum amplitude estimation. So now if you do uniform superpositions over all your solutions and you estimate the amplitudes of those, of course, you can also infer how many are there. So you can also do solution counting with that. And another example is in linear algebra. If you're familiar with the HHL algorithm, even if you're not familiar with it, it's still used in there. So they also use amplitude amplification within the HHL algorithm to also boost amplitudes of their solution vectors. And there are way more. So I could probably fill the whole talk with just applications of Grover's algorithm in different areas than unstructured search. And in my opinion, at least, on others' opinions too, those are actually practically relevant areas, unlike unstructured search. So I hope I've convinced you that Grover's algorithm is something worth handling with care, and also that all these problems are actually classical problems, as I mentioned in the beginning, right? So there's a lot of classical structure going in there, and all ingredients of Grover's algorithms, the oracle, so on and so forth, are with respect to this classical structure. So you want to express them also with respect to this classical structure, and this was the main motivation or the main guideline for this programming language design is reuse classical methods whenever possible. So if I have a function, classical function that describes what I'm looking for, I also want to use that same notation somehow in the quantum context and make it make sense in the quantum context. That is the main idea. Then another slightly messed up slide about the comparison of classical computing and quantum computing. I mean, this is very beginner stuff. Again, was a bit tailored to the computer scientists who don't know so much about quantum computing. But I mean, if you just compare them one by one, it's very, they're again very similar, right? Classically, you have a bit, can be 0 or 1. You have n-bit registers as the n-fold Cartesian product of these single bit. Logical gates are simply functions from bit strings of length n to bit strings of length m. Doesn't have to be the same length on both sides. And of course, you can always infer or you can measure the state of your bit, right, without disturbing the system. Then comparison, quantum computing basics. Okay, you substitute the bit with a qubit. You substitute the n-bit register with an n-qubit register, which is then the n-fold tensor product of the single qubit systems. The quantum gates, at least the unitary ones, they map n-qubit registers to n-qubit registers, so we don't have different length on both sides. But of course, you can throw away qubits, so you can also go or you can add qubits that were not affected. So in practice, you of course can also vary the number of qubits from left to right. And And I mean, the main striking difference is, of course, the measurement stuff. In classical computing, don't really have that issue that if you inspect the bit state that you disturb the system. But here, of course, you have. So you have to be careful with measurements. Measurements are indeed one of the few things that have to be added on top of all the classical language in order to elevate it to a quantum programming language, right? There's no classical analog of measuring in that sense. Okay, that's very messed up, but I think you can still see it. It's a very basic definition of a unitary that is supposed to be the quantization of a Boolean function f. So the Boolean function f now goes from bit strings of the same, of length n to bit strings of the same length. And so u is called a quantization of f if for every bit string, if I apply u to the corresponding computational basis state, then I get out the computational basis state that corresponds to the image of x under f, right? Very basic definition, very simple. And in turn, then we say a logical function is quantizable if such a quantization exists. And what you can very easily see is that this can only be the case that a function is quantizable only if it's bijective, because if it's not bijective, then it's especially not injective, and I just have two computational base states which end up on the same computational base state. If I apply u, that's definitely not unitary. So f has to be bijective in order to be quantizable. Okay, still looks good. So now I want to discuss a bit how to make classical functions bijective or reversible. I mean, this was luckily a topic that was addressed roughly, I don't know, 20, 30 years before quantum computing started. It's called reversible computing. And we can borrow a lot of techniques and insights from there already. So people already date with that. And then we can just elevate those to design of quantum circuits, so on. I mean, those are the four most basic gates I can think of classically. The NOT gate, of course, is already bijective, right? You only need one on one bit, and you have a bijection. The XOR gate, you need to restore one of the input bits in order to make it bijective, right? You cannot map 2 to 1, that's not bijective. But if you just keep one of the inputs alongside, then that's already bijective. For the AND and OR gate, you have to add one additional bit, simply because there are too many. For the AND gate, for example, there are three input pairs that evaluate to 0. So you cannot make that bijective by just keeping one of the input pair. You actually have to keep both of them, like both input bits, and store the result in an additional one. Same for the OR gate. But importantly, you can make all of them bijective. That's very important. And you can deconstruct or decompose all other classical functions and these bitwise functions in terms of these elementary gates, which means if you can make them those bijective, you can also make every other logical function bijective or / reversible. And they're like very nice decomposition techniques stemming from the field of reversible computing that do that, which in turn means we can actually quantize every logical function. I mean, this is no surprise, right? A quantum computer can, in principle, do whatever a classical computer can also do. But the nice thing is here that you can use on the classical side well-established decomposition techniques that don't even care whether in the end you put it on a quantum computer or not, but just they're formulated in terms of this reversible computing area where you already want to minimize ancilla bits and gate depth, but purely on the classical side before you put it on the quantum computer. And this adds a bit perspective to this. This was about gates. Second, it's about how we interpret quantum states or multi-qubit states. We basically have three options. We can either interpret it as a superposition of bit strings, and then we can talk about bitwise operations. We can interpret it as superposition of signed or unsigned integers via the binary representation, right? I can write, in a certain range, I can write my integers as in binary representation as bit strings, and therefore also identify my quantum state as a superposition of integers, unsigned or signed, however you want. And with this, then I can also talk about addition and subtraction on a quantum computer. I can give meaning what it means to add to quantum states, right? You don't add the vectors in the Hilbert space, it doesn't make sense. but you add the bit string or the binary representation of the integers represented in there. Those you add together, and this you can do in superposition. And again, there are a lot of work has already been there, and I don't want to go into detail there. But what you can nicely do is, for example, quantum addition and subtraction. You have to keep one of the inputs in order to make it unitary. For that's, I mean, there are very lot of techniques to do that. One of them I like a lot is with quantum Fourier transform in the middle, where you apply the quantum Fourier transform. Then you just do some rotation negates, right? You add phases rather than adding amplitudes, and then you do the QFT inverse, and this is how you can very efficiently implement quantum addition and subtraction. Subtraction just by subtracting phases instead of adding phases. Quantum multiplication also works. You need an additional register simply because if you multiply with 0, right, you always get 0 out. So the multiplication itself is not even invertible. So you first have to make it invertible by adding an additional input, and then you can quantize it. That's the similar idea. And then, so this construction, if in the ancilla register, the Z, you initialize it in 0, then of course you just get the product of X and Y in the ancilla register, and you keep the inputs in the others. In quantum division, modular operation also works, but that's very tedious and complicated because you have to keep track of the signs of different representations. So I don't give formulas here because they're very long, but also that works. So all the 4 or 5, it's debatable, elementary arithmetic operations are actually quantizable, and they're very optimized also for specific hardware optimized circuits to do that. So we also have a notion of arithmetic operations on quantum computers. And one more building block I want to discuss is quantum control. And luckily, those equations still look fine. What I mean by that is I want to apply some gate on some ancilla qubit A, and I want to condition it on another register being in a state that fulfills a certain logical formula, right? And the other register can, of course, be, or usually is, in a superposition of different computational basis states. And then I only want the ancilla qubit to be affected, in this case, by an X gate, whenever the computational basis state in the other register fulfills my formula. So this is this part. Whenever phi of X is fulfilled, I want to apply the X gate in the ancilla. And whenever it's not fulfilled, then I don't want to do anything in the ancilla, right? That's basic notion of controlled gates. But now we don't control on single qubits, but we control on Boolean formulas. Exactly what I just said. Unfortunately, those stay now there, but we will decipher it. I just want to go through 4 examples. The same examples I had before on that slide, the 4 elementary the elementary gates, so to say, classically. Negation is very simple. You just apply the gate before on the ancilla, and then you control on the formula. And so if the formula is fulfilled, that a gate gets applied twice and cancels each other out in this case. That's very easy. XOR is also very easy. You want the state or the bit string to fulfill exactly one of these formulas, either phi or psi. So you just apply them one after another, right? And if some state fulfills both of them, then again the X gate on the ancilla cancels each other out, right? It gets applied twice. That's simple. OR is super complicated, but let me still walk you through it. So the idea is you need 2 ancillas now. Again, OR and AND are a bit more complicated, not so compact. First, you store on the first ancilla, on the 0th ancilla, you store whether phi is fulfilled. Then on the second one, on the first one, if you start counting at 0, you store whether psi is fulfilled and phi is not fulfilled, right? You stored before on A0 whether phi is fulfilled. Now you negatively control on A0, and you control on psi in the main register. So A0 holds whether phi is fulfilled, A1 holds whether phi is not fulfilled and psi is fulfilled, but you want to check whether phi or psi is fulfilled. So in the end, you control once more the zeroth ancilla on the first ancilla. And then the result is in the end on the zeroth ancilla. And I mean, you just have to check 4 cases, right? If both are fulfilled, then A0 gets flipped to 1. A1 does not get flipped to 1 because A0 is already 1, right? You can really think on the basis of computation basis states. You can do it state by state. And that's a nice thing because everything is linear. Then this generalizes to being applicable in superposition. So you have in this case A0 is 1, A1 is 0. So the last one doesn't do anything, and A0 is 1. Perfect. And if only one of them is fulfilled, this also works. But it's, again, doesn't really have much to do with quantum computing. It's just classical logical reasoning in that sense. And lastly, the AND gate is a bit easier. You just, when you first store on an ancilla qubit whether phi is fulfilled, and then you check on the final ancilla qubit A0, you check whether phi and psi are fulfilled. That's way easier than the OR gate. So in summary, so far, what we have a bit-to-qubit encoding at the very basis, right? And then arising from that, we can quantize these logical bitwise functions by interpreting the computational basis states as bit strings or identifying them with bit strings. But we can also interpret them as integers and then quantize our arithmetic operations. And on top of that, we can also do quantum control statements very easily. And all the methods are really classical methods, just slightly elevated to the quantum case and applicable in superposition. And exactly. And now I want to talk a bit about the fundamental building blocks of every programming language there is, because it's not the syntax, it's a bit more. First one is the vocabulary. You have to think, okay, what tokens are actually part of my programming language, right? In C, for example, that's all the keywords, but all the comments, like how do I make comments in C? Or in Python, you can also think of Python if you want. But also variable names. What variable names are allowed? Those are all part of the vocabulary. Then you have to talk about, okay, how do I form sentences with those vocabularies? What are valid programs? At least syntactically, right? For example, I have definitions in Python, for example, def, then function name, then in parentheses, maybe some arguments, and then colon. That's the sentence in that sense. That's syntax. Semantics, then also you have to, I will give an example later. For example, defining some integer and setting its value to 3.5 is syntactically correct, but not semantically, right? You cannot set an integer to a float value. And then when you have all that, so to say the language is sound, but then you generate some source code and you want to optimize it for hardware or for further transpilation, because in the end it always has to get mapped down to a language that the computer, whether it's classical or quantum, actually understands, right? The computer doesn't understand Python or C, it stands strings of zeros and one. You have many translation layers from your high-level language down to this very low-level bit stream. And for each of these points, there's one, so to say, one part of each compiler that does this. First one is called a lexer, just reads in your input stream and tokenizes it and warns you if you wrote something that's not legal. Then the parser creates, we will see that in a minute, creates some tree out of the tokens and checks whether that's syntactically correct. Then semantic analyzer, who goes through that parse tree and checks, okay, does it even make sense what the programmer wrote there or not? And then, okay, the optimizer does the optimization, and the translation is done by instruction mapping. So you have a dictionary, so to say, which tells you this instruction, this language corresponds to those instructions in the other language. It's usually more low level. And for CQ, I implemented at least the first 3 steps. Let's see whether we continue also with the other tools. So if you're interested, hit me up. And let's make some lightweight examples of lexer and parser and semantic analyzer. So the lexer, as I said, tokenizes the input and eliminates like white spaces and comments. So for example, I have in C syntax now, int a equals true, and then I have some comment. This just gets split up, right, into int a equal true semicolon. But the comment, for example, gets eliminated by the lexer. And then if you want to code that, actually you have to tell the lexer what what tokens are allowed. For example, as identifiers, one does this with regular expressions. Usually I have this funny looking thing. My Boolean constants are false and true, right? There are no more Boolean constants, but those then get recognized by the lexer. So that's rather easy to write, this lexer. And for CQ in particular, I added 3 more keywords to the vocabulary of C, namely measure, right? There's no classical analogon of that. Phase, we also need to address the phase directly. That's also not really with the classical analogon. And quantum, to declare something as a quantum variable. Those are the 3 additional vocabulary or 3 additional keywords. Everything else is as in C. So it's the same words, integer, float, whatever. Those are all the keywords borrowed from C. Then the parser does the second step. It takes this stream of tokens now, this tokenized stream, and constructs a parse tree. Let's stick to this example, right? I have int a equals true semicolon, and then I have some syntactic rules. In this case, there's a definition rule which says, okay, first comes a type, then comes an identifier and a sign, then some initialization value, and then a semicolon. Then it checks, okay, that perfectly matches that rule. So I construct a parse tree with a def node in that sense. So the nodes have the name of the syntactic rule I apply, and its childs are the actual components of that statement. Here I listed all or some of the additional rules. There are a lot of rules for CQ, right? Because you have to introduce additional rules. What happens, like how do you define quantum variables? Where can quantum variables appear? So on and so forth. There's a lot of additional rules, but those are some example ones. I won't go into detail here. Then comes the semantic analyzer, which is even more complicated for this hybrid language, right? Because you can, just from the syntax, you could write now a lot of weird stuff, right? You could start measuring classical variables on so on and so forth. You cannot really forbid that just with the syntax, but this is where you have to impose semantic rules. So in this case, integers can only be assigned integer literates. That's a meaningful rule, I would say. So this parse tree is semantically incorrect, right? The parser will not check that, but the semantic analyzer will go through the parse tree, has this list of rules, and then we'll say, okay, that's nonsense, and that's not a valid program semantically. And here are the additional rules. I will not cover all of them, but maybe some of them, because to discuss that, they actually make sense, right? For example, classical variables cannot be assigned quantum values. Makes sense. Other way around, it makes sense. Function is quantizable if it returns classically or void, only inputs classical parameters, and has a quantizable function body. We will come to that in half a minute. Same with unitary. There's also a notion of unitarity for functions. Phase and measure can only be applied to quantum variables. I can call a quantizable function also with quantum parameters instead of classical ones. And the other ones I will skip for now. And because I want to focus really on this quantizable or unitary flag, because I think it's a cool idea. Not my idea, but in general, it's a cool idea. So how do you determine whether a function is quantizable, whether you can elevate it to something you can execute on the quantum computer? Ideas to do that recursively with some blacklist approach. So you have some statements which, as soon as they appear, the whole body that contains them is not quantizable, right? And then this propagates through the whole function body and renders the whole function not quantizable. And everything that does not have any entries from this blacklist is quantizable. That's way easier than to check, so to say, constructively whether something is quantizable. So the idea is here, f is quantizable if return and parameters are classical, I already mentioned that, and the function body is quantizable. In this case, this works because it returns a classical integer and takes in a classical integer. Perfect. Now let's check whether the function body is quantizable. The function body is quantizable if and only if all statements are quantizable. So we have to go through all the statements in the body. The first one is an assignment. It's quantizable if and only if the left-hand side is classical and the right-hand side is quantizable, right? I can update values only by something that's quantizable, because later I want to exchange the left-hand side by a quantum variable. I want to do an update, so the update has to be quantizable itself. That works. Plus equals 1 I can do. So adding 1 is quantizable. So the whole assignment already is quantizable because the left-hand side has a classical variable. Next one, the if-else statement. That's quantizable if all expressions and all branches are quantizable. Now we have to go one layer deeper. The comparison, so I'm now at if a equals or is bigger than 5, this is quantizable if left-hand side and right-hand side are quantizable. I think you get the idea, right? And then you just check, okay, a, that's just a variable, that's a quantizable expression, and 5, it's a constant, that's quantizable, nice. So the comparison is quantizable. Then I have 2 return statements. They are quantizable if the return value is quantizable. In this case, they are. It's a constant, -2, and it's a. That's a single variable with no measurement or anything weird stuff, so that's quantizable, which means everything's quantizable. Amazing. So in this case, the whole function is quantizable. And of course, it looks a bit tedious to do this by hand, right? But you have to program. You have to teach the computer somehow to evaluate that. Let's do one mini example where this fails. For example, I have here in the else statement a while loop, and I said, okay, while loops are not quantizable, right? Because you have to check, you have to evaluate a condition all the time. It doesn't seem very quantizable. So in this case, that's not quantizable. So this fails. Now all expressions and branches are quantizable. It's not true anymore because the else branch is not quantizable because of the while loop. So this propagates now. If else statement not quantizable. Not all statements are quantizable, therefore the function body is not quantizable, and therefore the whole function is not quantizable. So such that you can like have an example for both a quantizable and a non-quantizable function. And the same thing works for the unitary flag. We have a bit different rules there, but it's the same idea. And with that, we are already on the level that we can discuss existing programming languages, and I want to do that. Namely, I want to focus on Grover's algorithm, the main motivation. And with some Oracle function, in this case, I took a very easy one. I just evaluate whether a number is odd. In this case, I return true. Otherwise, I return false. Very, very easy Oracle function. And let's go through some of the existing classical quantum programming languages. First one is Quipper. And I sorted them, you will see, I sorted them by the amount of I would change something in there. But I have to be, so I'm a big fan of C, therefore I'm not a big fan of functional programming. Therefore, of course, the functional programming language was the last one, or my least favorite. But I mean, it's still good language, just not for me. And I highlighted here the things that I would like to change because, in my opinion, they're too low level, right? Now it's just a matter of taste. This works. Has a perfectly implemented backend. You can actually write programs in that language, compile it, and you get out circuits. So it's perfectly valid, perfectly fine language with nice backend. But what I don't like so much is how low level it is. So first I have to talk about qubits directly instead of integers, for example, but I want to do something with integers, in my opinion, in my case. And I have to talk about gates. So I have here a Z gate that's applied. I have Hadamards that are applied. Q not, so it's a not gate. Then I have another Z gate applied, controlled on something. And again, like Q not, Hadamard, so on and so forth. So in my opinion, for my taste, a bit too low level. Let's go to the next one. QCL, I forgot what it stands for. That is a bit more C-like, so it's not functional anymore. That's good. But again, very low level, right? I have to talk about Hadamard gates. I have to talk about NOT gates, phase gates, and then again, Hadamard gates, controlled Z gates, so on and so forth. But a bit more high level or a bit less functional. That's good. OpenQASM, that's again very low level, but of course on purpose, right? It's meant to be a quantum a quantum assembly language. And no surprise, there are low-level statements in there. So OpenQASM, for example, is the backend when you write something in Qiskit, it gets transformed to OpenQASM stuff most of the time, and then this code then actually gets executed on IBM machines. So the IBM machines understand, on other machines too, understand what OpenQASM code means, how to translate it into actual hardware gates that run on hardware. But again, I have Hadamard, Xgate, Control Z. Let's get rid of that. Q sharp is, that's more high level, but also very long, right? If you compare, it's way longer. But because we can define nice functions in it, but we still have some gates left. So we don't want them. So we have Z gates, Hadamard, Xgate. And what I forgot to mention, all of them, let me go back. In all of them, the oracle function that I talked about, I had to implement it explicitly on a gate level basis, right? For Quip, I have the oracle, and you cannot see what the oracle was in the beginning, right? It doesn't look like a test for odd numbers, right? It talks about applying a Z gate somewhere. That's a bit weird. But it is, in the end, it will be the correct oracle, right? But you cannot see from it what you want to do with this. So this is my main point of criticism in that sense. And sorry, again, in QCL, same way, right? Where is it? There. In the main Grover procedure, exemplary oracle function, again, have to apply Z-gate. Doesn't have anything to do at first glance with testing for odd numbers. Also in OpenQASM, also in Q sharp. Exactly. Where is it? Somewhere. Yeah, up there. Yeah. There's also, again, this Z-gate applied, right, to the 0th qubit. Now let's come to a language that's actually way cooler, Silk. I also found about it recently. And here, what's gone is that I have to express the oracle in terms of gates. Here, in the first part, line 4 to line 6, doesn't this look amazing? You check the candidate, you do a bitwise AND with the number 1, and then you check whether the result is 1. And if you think that's exactly what an odd testing for an odd number is, right? You just check the last position whether there's a 1 or not. So that's way cool, and you can then they have this lifted keyword. You can lift that to a quantum function, and then they also have something what I presented to you with this quantizable flag for functions. They also have something implemented, right? I cannot just write whatever I want in there, because then the compiler will complain, say that's not liftable in their language. So the only thing that still remains, or what bothers me here, is that I again have Hadamard gates, right? If I want to do the uniform superposition in the beginning of Grover's algorithm, here I still have to talk about Hadamard gates. So also let's get rid of that. Let's say the final ingredient of CQ is the square bracket notation, and the idea is the following. It's fine. So let's take a quantizable function f, which inputs an integer and outputs a bool. And let's define the square bracket, f enclosed in square bracket should be the quantum circuit, or a quantum circuits, there are several, right? Which maps the 0 state to uniform superposition of all computational basis states j, for which f of j evaluates to true. So I will repeat that, it's a uniform superposition over all computational basis states whose labels, when I plug them into f, right, their labels are integers, so I can plug them into f and I get true in return. And over this I build a uniform superposition. And for this I introduce this square bracket notation. And then with this comes, say, two pieces of syntax. I can either initialize a quantum variable, quantum int y equals square bracket f. This initializes the variable y in a uniform superposition over all of these computational basis states. Or I can apply that circuit, I mean it's a fixed quantum circuit, I can apply that to an already existing variable, right? That's also important for Grover's algorithm, because in the beginning you create a uniform superposition via all Hadamards, but later on you apply these all Hadamards. You don't initialize something again. So you really need both syntaxes, but both are captured with this square bracket notation. And with this, we finally come to the formulation of Grover's algorithm in CQ. It looks very similar to Silk, right? The oracle looks nearly identical. It's just that I don't have this quantizable flag explicitly, but it's checked implicitly by the compiler. So I don't have to write quantizable, it's checked. And then what's new is the line 9 to 11. in this case, the function is very boring. It's the function that returns true because I want a uniform superposition over all computation-based state. So no matter the input, I always get out true. And if I take the uniform superposition over that, I get all computation-based states. But now I can rewrite the main part is exactly this. I initialize the state in the uniform superposition, line 14. Then I do my outer loop, right? I have some number of iterations. That's classical. If the oracle of the state equates to 1, this is this quantum control we talked in the beginning, then I want to apply the phase, right? The phase I have to do somehow explicitly. Then I do the layer of Hadamard's with this new syntax. Then I do the reflection around the zero state that you also have in Grover's algorithm. There you can just check whether the state is not equal to 0. And then again, you apply the layer of Hadamard gates. And in the end, you measure. And this you return. And so this is very similar to the Silk formulation. But the nice catch is now you don't have any explicit gate anymore. I like that at least. But it's, of course, it's a matter of taste. So to summarize the language itself, so what I have introduced, there are 3 additional keywords, right? Measure, phase, quant, because they don't really have classical analogs. Then the logical and bitwise functions, they are quantizable. Arithmetic operations, you can also write, you can add 2 quantum variables together. That's fine. It's overloaded, so to say. If else and switch statements, you can quantize, and we saw some example. Right, you have to make sure that all branches are quantizable and all the conditions are quantizable, and then the whole thing becomes quantizable. We have this quantizability and unitarity flag, and last but not least, the square bracket notation for uniform superposition. So that's a nice conclusion slide, but I want to add one more thing, namely ongoing work of actually implementing the circuit synthesis from a description of a function f to the square bracket notation, right? How do I actually get the quantum circuit that implements that, right? It's not clear. I mean, I can define whatever I want in my language, but the compiler should also, in the end, spit out a quantum circuit that does that. In the literature, there are examples for different classes of functions. One of them is fixed Hamming weights or Dicke states. I think they are the most prominent ones. There's a very nice circuit that does that. You can also, if you don't want all computation-based state, but just a consecutive subset, there's also a very nice circuit for that. And also, you can also do uniform superpositions over permutations in whatever representation you want. That's all possible, but it's not general. It's not for each f there's a clear rule. So and here comes in a bachelor thesis that I recently supervised. Moritz also here today. Was very fun working on that. We tried to tackle, so to say, general formalism. I input function f in what format whatsoever, and I get out a quantum circuit that creates the uniform superpositions over all computational base states whose label fulfills this Boolean formula, this logical formula. And what we achieved, or what he mostly achieved, is, for example, I can give him a list of numbers, of bit strings whatsoever, and it's very easy to come up with a circuit that does the uniform superposition over these numbers. But what he also did, he optimized it, right? He formulated as a optimization problem, classical one, right? And then the classical optimizer can optimize the cycle and gate count for that circuit. That was a nice thing. So of course, in the end, one had to solve a TSP problem. Then also for very elementary logical operations, we have clear quantum circuits that do that. And for disjunctive normal form, at least we have a non-uniform approach. So you can get all the feasible, all the computational basis states in superposition, but not uniformly, right? That's way harder, and we're still working on that. But at least it's a good starting point, I would say. And with that, I would like to conclude. Here's again the QR code in case you're interested, and thank you very much for your attention.